Welcome to the lecture series by MSP on the chemistry of main group elements. In my previous lecture, I spoke about the valence bond theory, essentially based on hybridization concept and its utility in main group compounds to understand structure and bonding, including the geometry and shape. Today, let me continue the discussion on structure and bonding and proceed to another important bonding theory, that is molecular orbital theory. Before that, let me say about the limitations of valence bond theory, and of course, we saw valence bond theory using hybridization concept very effectively explains the geometry and shapes of most of the molecules of main group compounds and to an extent transmetal compounds as well. But however, there are some serious limitations of application of valence bond theory as far as coordination compounds are concerned and to an extent in case of main group compounds as well. What are the limitations? Let us look into those things and proceed to the next molecular orbital theory concept. The major limitation of valence bond theory is it does not explain the color of the compounds, that is spectral properties, and also it does not explain fully the magnetic properties. Okay, for example, the temperature dependence of magnetic properties and all those things are not fully explained, okay, and it only gives an idea about calculating spin only magnetic moment values. And in general, valence bond theory gives more emphasis for localized bonding concept. So, in view of this one, okay, molecular orbital theory was proposed and it takes all the best parts of valence bond theory, VSEPR theory, crystal field theory, and made it very refined theory to explain almost all aspects concerned with the main group as well as transmetal compounds and their reactivity as well. Let us start looking into those things. Keeping in whatever I mentioned about the previous structure and bonding concepts we came across, it is always ideal to consider more than one theory or one concept to explain the complex phenomena that occurs in a molecule, in particular bonding. According to valence bond theory, molecular shapes are essentially based on the interaction of atomic orbitals, which results in new hybrid orbitals and which can explain both sigma bonding as well as pi bonding. Whereas molecular orbital theory essentially deals with the orbitals associated with the whole molecule, that is we call it as molecular orbital, that results due to the combination of atomic orbitals of the atoms that are combined to make a molecule to explain the energy and behavior of a molecule. This is the major difference between the valence bond theory and molecular orbital theory. Okay. And molecular orbital theory is based on delocalized bonding model. That is very important, and similar to isolated atoms, a quantum mechanical treatment is adopted for molecules as well, uses the concept of molecular orbitals and here considers the wave-like properties of matter. So, let us look into the themes of molecular orbital theory. A molecule is considered on a quantum mechanical level as a collection of two or more nuclei surrounded by delocalized molecular orbitals generated as a consequence of mixing of atomic orbitals. That means, atomic wave functions are summed to obtain molecular wave functions. If wave functions reinforce each other, that is couple each other, a bonding MO, bonding molecular orbital is formed. That means, the region between the two nuclei where high electron density exists, okay, in molecular orbitals, that is called bonding molecular orbitals. If wave functions cancel each other, an anti-bonding molecular orbital is generated. That means, a node or a region where 0 electron density exists between the nuclei is also referred to as anti-bonding molecular orbital. We should remember, when atomic wave functions are summed up, we get bonding molecular orbitals. When the atomic wave functions are subtracted, an anti-bonding molecular orbital is generated. You can see here in this picture, okay, in the first one you can see clearly this is due to the summation of that atomic orbitals. Here a bonding molecular orbital is generated. So, amplitude of waves wave functions are added here. So, amplitude of wave functions of two nucleus interacting together is added, whereas in this case amplitudes of wave functions are subtracted. So, amplitude of wave functions are subtracted. So, this represents anti-bonding molecular orbital and this represent the bonding molecular orbital. Okay. So, let us look into the contours and energies of the bonding and anti-bonding molecular orbitals of a simple diatomic molecule such as H2. So, here we are considering the 1s orbital of hydrogen atom. So, they are interacting. So, that means here when you sum up the wave functions of both the atoms are added, okay, so that and or they can be subtracted. When they are added, it generates the bonding molecular orbital where the electron resides between these two nuclei, whereas here anti-bonding molecular orbital is generated and here a nodal region, that means 0 electron density exists between the two nuclei. Okay. And of course, when we combine two atomic orbital, bonding molecular orbital always have much lower in energy, whereas the anti-bonding molecular orbital will be having higher energy than the energy of two atomic orbitals that are combined in generating these two bonding and anti-bonding molecular orbitals. For example, if two atomic orbitals are here and you are generating two molecular orbitals, one is bonding, another is anti-bonding, this will be much lower in energy than these two and this is higher in energy than these two. To draw a MO diagram involving say 4 set of orbitals, we have to consider 3 sets of atomic orbitals and 1 set of molecular orbital. For example, let us consider the case of CF4 or CH4. We have to consider here 5 sets of atomic orbital, that means 4 sets of atomic orbitals are coming from 4 fluorine atoms and 1 set is coming from carbon, and then that generates 1 set of molecular orbitals. Similarly, if you consider sulfur hexafluoride, we have to consider 7 sets of atomic orbitals, 6 from fluorine atoms and 1 from sulfur to generate 1 set of molecular orbitals. So, this makes MO diagrams much more complicated and difficult to both construct and interpret. That means we find a solution to simplify it. So, how to simplify it? So, resolving MO description, in particular polyatomic molecule, into a 3 component problem using a method known as ligand group orbitals. Of course, ligand group orbitals are extensively used in coordination compounds. So, let us consider a linear triatomic molecule having composition XH2 oriented along Z direction. So, consider two 1s atomic orbitals of two hydrogen atoms. Each 1s atomic orbital has 2 possible phases, and when they are taken as a group, they are essentially 2 possible phase combinations. They essentially leads to 2 possible phase combination. Essentially, they are called ligand group orbitals. So, these phase combination, 2 possible phase combination that results is nothing but ligand group orbitals. So, number of atomic orbitals combined is equal to the number of molecular orbitals generated or produced. For example, if I am using 4 atomic orbitals, okay, and then I will be having 4 molecular orbitals, out of which 2 may be bonding, 2 will be anti-bonding. The energy of bonding molecular orbitals will be lower than that of the isolated atoms. The energy of anti-bonding molecular orbitals will be higher than those of isolated atoms. So, the energy and the orientation of atomic orbital should be similar to form molecular orbitals. That means, when we are combining 2 atomic orbitals from 2 isolated atoms, their energy should be comparable. For example, energy should be somewhere here or here, it should not be something like this. In this case, essentially the effective molecular orbitals cannot be generated because the energy difference between these 2 combining atomic orbitals will be quite considerable. So, in that case actually there is no bonding takes place. So, representation of sigma and pi bonding is very similar to valence bond theory, whereas in case of molecular orbital theory we are using asterisk, that is star, to denote anti-bonding molecular orbitals. For example, if I say simply sigma, it is bonding orbital, and if I put a superscript star, sigma star or pi star, essentially they represent anti-bonding molecular orbitals. While filling molecular orbitals, they are generated as a combination of atomic orbitals. Similar to atomic orbitals, Aufbau and exclusion principles and also Hund's rules are strictly followed. Okay, that means whatever the method we are following, rules we are following while considering the filling of the atomic orbitals of isolated atoms, the same strategy is used while filling molecular orbitals with the electrons that are coming from the both the combining atoms. So, higher the bond order, stronger is the bond. So, bond order equals number of electrons in the bonding molecular orbitals minus number of electrons in the anti-bonding molecular orbitals divided by 2. Bonding and anti-bonding molecular orbitals for core electrons cancel each other. For example, if I take 2 electrons from one atomic orbital and 2 electrons from another atomic orbital, and I generate 2 molecular orbitals, one here, both of them will be having 2 electrons each. As a result, net bond order is 0. That means does not exist any bond. That is what it says. The bonding and anti-bonding molecular orbitals for core electrons cancel each other. As a result, we are not considering them towards net bonding in a molecule. That means there is no net contribution coming from the core electrons. Only MO diagrams showing molecular orbitals created by combining atomic orbitals of valence electrons are very important. That means when we look into the reactivity of the molecule, bonding, bond strength, we have to consider or give emphasis only for the atomic orbitals having valence electrons. Let us draw MO diagram for simple molecules such as H2, and then we can continue writing for other higher polyatomic molecules. Let me start with the simplest diatomic molecule, that is H2. So, in case of H2, we are considering 2 hydrogen atoms having 1 electron each in their respective 1s atomic orbitals. This is energy. So, here this is 1s and this is 1s, we have 1 electron each. Okay. So, these two will combine together to generate 2 molecular orbitals. So, this is called sigma 1s is bonding molecular orbital. This is atomic orbital of H, and this is atomic orbital of H, and this is molecular orbital of H2. So, this is how one should write, and now these 2 electrons will come here and bond takes place, and next here it is sigma 1s star. This represent anti-bonding. So, if you calculate the net bonding in this one, bond order equals half 2 electrons minus here 0 electrons equals 1. So, net bond order is 1. So, that one should write H2 molecule as HH. So, this is how one can write MO diagram for H2 molecule. So, let us predict the stability of some molecular as well as ionic species using the same molecular orbital diagram. Now, I am considering He2 plus. So, that means I am not considering He2, I am considering He2 plus. That means we have 2 helium atoms, one comes with 2 electrons and another one comes with 1 electron. Okay. Of course, always we should remember to write here 1. So, here I am considering atomic orbital of helium. Here 2 electrons are there. Here I am considering atomic orbital of helium plus, that means 1 electron is removed. So, we have only 1 electron. Now, I should construct MOs. So, 2 atomic orbitals are combining to give 2 molecular orbitals, one is bonding, one is anti-bonding, and again same sigma 1s and sigma 1s here. So, I am putting 2 electrons here. So, now we are left with 1 electron, this will go to anti-bonding. Okay. So, now let us, this is MO of He2 plus. Okay. So, now let us look into the bond order, equals 2 electrons here minus 1 electron divided by 2, here it is half, bond order is half. That means, this He2 plus can exist, here it can exist. Okay. If I have a question says predict whether He2 plus species exists or not. Since it has a net positive bond order, it can exist. Let us look into now He2. Okay. So, again here what I am doing is I am considering both the helium atoms having 2 electrons each, another one here, 1s. So, atomic orbital of He, atomic orbital of He, and here I am writing MO molecular orbitals of He2. Okay, so, here 1s, here 1s, this is okay. So, 2 electrons are here and 2 electrons are here. So, now let us look into the bond order, equals 2 here and 2 here by 2 equals 0. Okay. So, cannot exist. We can simply conclude that He2 cannot exist. Okay. So, this is how you can predict using simple MO diagram whether a molecule can exist, a molecular ionic species can exist or not. So, let us continue with this exercise. Using MO diagrams, predict whether Li2 and Be2 can exist or not. The question is, using MO diagram, predict whether Li2 and Be2 can exist or not. Okay. So, let us look into now Li. Okay. So, what we have is here the same exercise we should continue. This is, it represents energy. We are now considering the valence shell of lithium having 1 electron in its 2s orbital. Okay. And similarly, we are also considering 2 such lithium atoms having 1 electron each, and they combine together to form 2 molecular orbitals. This is sigma 2s star, whereas this is sigma 2s. So, we join them, and in homodiatomic molecules, the energy of both the atoms that are combined will be having the same energy, and these two will be equidistant from both the atoms. This distance will differ depending upon the electronegativity difference of 2 atoms that are combining. Those cases comes when we look into heterodynamic molecules or polyatomic molecules. So, now we have 2 electrons here and no electron here. This is atomic orbital of lithium, this is atomic orbital of lithium, and this one is molecular orbital of lithium 2. Okay. So, that means here if we calculate the bond order, that is equals to 2 minus 0 by 2 equals 1. So, can exist. Okay. Can exists. Okay. So, now let us look into beryllium 2, that means diberyllium molecule. Same exercise we should follow, and in case of beryllium we have 2 electrons in the valence shell, that is the electronic configuration is 1s2 2s2. We have 2 electrons. We are combining to make 2 molecular orbitals. So, this is sigma 2s star, this is sigma 2s. So, these 2 electrons will come here, another total of we have 4 electrons. So, here atomic orbitals of beryllium, atomic orbitals of beryllium, and here MO molecular orbitals of beryllium 2 plus. Okay. So, now let us look into the bond order, equals 2 here minus 2 here divided by 2 equals 0. So, we can simply say beryllium, diberyllium cannot exist. Okay. So, this is how we can easily write the electronic configuration. From that one we can derive the molecular orbitals starting from the corresponding atomic orbitals, and we can say, we can talk about bond order, and also we can conclude whether this molecule or ionic species exists or not. So, now I would show you the contours and the energies of sigma and pi molecular orbitals through combination. If you just look into the previous diagrams, just I made box diagram and I wrote actually how these electrons in a particular orbital interact while generating molecular orbital. For example, I have considered 2p atomic orbital in this case. You can see the diagram I have shown here. Okay. 2 such 2px atomic orbitals are oriented in this fashion from 2 atoms, and here this is called end to end overlap or head to head overlapping. Essentially always this end to end overlap or head to head overlap results in sigma bond formation, and again one can write bonding molecular orbital as well as anti-bonding orbital. So, how these contours appears can be visualized from this diagram here. You can see when the wave functions of both px are added here, it generates a sigma 2p molecular orbital having the electron density residing at the middle of 2 nuclei. Okay. Whereas, in this case when you subtract, it generates anti-bonding molecular orbital, that is sigma star 2p, where a node or 0 electron density exists between 2 combining nuclei. So, this is how one can show the contours and energy of sigma molecular orbitals. In the next slide I will be showing you the pi. Hope it is clear for you. So, here 2 are combined together to generate bonding molecular orbital, and at the middle where the bulge portion is there, electron density resides there, and in this one you can see a node is generated where there is no electron density. This is sigma anti-bonding molecular orbital. So, since they are orthogonal to each other, if you bring 2 atoms close to each other, okay, if pz is interacting head to head, in that case remaining py and px orbital can have only the sideways overlapping. So, that means now side to side overlapping also results in covalent bonding, and that we call it as pi bond. You can see here when the wave functions of both of them are added here, it generates a bonding molecular orbital of this shape here. So, this is called pi 2p molecular orbital bonding. Similarly, here electron density resides, whereas here a node is generated between the two combining orbital, and this is called pi star 2p molecular orbital anti-bonding. So, you can just differentiate between the sigma and the pi using these diagrams. So, these diagrams clearly show the contour and energies of sigma as well as pi molecular orbitals generated through the combination in different orientations. Okay. So, let us look into the relative energies. Okay. The relative energies will be in this order: sigma 2p is less than pi 2p, is less than pi star 2p, less than sigma star 2p, and there can be some variation. In end-to-end interaction, the bonding is more effective. That means, sigma bonding is much more stronger compared to the pi bonds. Okay. So, end-to-end interaction, the bonding is in end-to-end interactions, the bonding is more effective and bonds are much stronger compared to the side-to-side bonding. So, relative MO energy levels for second row homonuclear diatomic molecules I am going to write down now. So, that will give you some idea. For example, let us consider diatomic molecular species of all elements in the second row. Of course, first one should write energy here. First I am considering O2, F2 and Ne2. Okay. So, here what we have is 2p and another 2p. Since it is a diatomic homodiatomic molecules, the energy should be same. Okay. So, here essentially it splits into sigma component as well as pi component. We have here sigma and then we have here pi, and similarly we have here sigma, and of course, here sigma star 2p and it is pi star 2p and sigma 2p and pi 2p. So, I can just show them like this. Because of lack of space, I have brought them close to each other. It does not mean that they are much closer in this one. It is not according to some scale, because I have to write MO diagram for 2s as well. Here we have sigma star 2s and so this diagram holds good for diatomic species generated for oxygen, fluorine and neon. So, in my next lecture I will be discussing about the remaining second row elements such as boron, carbon and nitrogen, that is B2, C2 and N2. What would happen in those cases, whether they have similar energy order or there will be some difference, and let me discuss all those things in detail in my next lecture. So, I have a present reading. Thank you very much.